We've already talked about electric force when we have only 2 charges. In this problem we have 3 charges that lie in a straight line. So here the problem reads 3-point charges lie along the x-axis at 0, 5, and 8 centimeters. If the 3 charges are positive 5, positive 4, and negative 9 microcoulombs respectively, what is the net force on the middle charge? And it says to be sure to include a direction. Whenever asked for an electric force or any kind of force, we always want to include a direction with that. So here we have at the origin at 0 centimeters, and the next charge is at 5 centimeters, and then the next charge is at 8 centimeters. So we have our 3 charges. The first charge is for 5 microcoulombs. Now I'm not going to label this as charge 1. I think it's easier if we actually label this as charge 5. 5 to designate that it is a 5 microcoulomb charge. It'll make it easier when we actually put our numbers into our problems if we label the notation to be the same as the amount of charge. So the second charge here I will label as Q4 for positive 4 microcoulombs. And the last one I'll label as Q9 for negative 9 microcoulombs. We're asked to find the total force on the middle charge. So I like to put some kind of a box to notate that this is the charge that we are asked to find, or the total force on this charge. So this charge is being pushed or pulled by 2 others. Charge 5 and charge 9 are pushing and pulling on this charge. What we have to do is we have to find out how much does charge 5 push or pull on it, and then find out how much does charge 9 push or pull on it, and then add them together to get a total. Although charge 5 and 9 do push and pull on each other, we are not concerned with that. All we're asked to do is find the total force on charge 4, so ignore the interaction between charge 5 and charge 9. Okay? And what we're also asked to do, I know that these charges will eventually move. What we're really trying to find is the total force on charge 4 at this moment in time. Not later on when they start to move, but what is the total force on charge 4 at this moment? So the first thing we need to do is we need to find the force on charge 4 because of charge 5. And so my notation is going to be F45. This says the force on charge 4 because of charge 5. So again, this is the force on charge 4 because of charge 5. And so my equation is K times Q4 times Q5 divided by R squared. So it's my Coulomb's constant. I'll just write it as K. It's 8.99 times 10 to the 9th newtons times meter squared per coulomb squared. Charge 4, again, is 4, in this case, microcoulombs. So micro means negative 6. Charge 5 is 5 microcoulombs. So again, micro means negative 6. So we see that the notation that we write it as, it makes it easier when we put our numbers in. Now the distance between them, if I go back, charge 5 is at 0, charge 4 is at 5 centimeters. So the distance between them is 5 centimeters. This distance is 5 centimeters. So we put in 0.05 meters. Of course, we have to convert that. We get this force on charge 4 because of charge 5 to be 71.9 newtons. But we need a direction. Now these 2 charges are both positive, which means that they repel each other. So that means that charge 5 will move to the left, and charge 4 will move to the right as they repel each other. But all I'm concerned about is charge 4, and this is why I put my box around it. So the force on charge 4, because of charge 5, is to the right. I don't care how charge 5 is moving. All I'm concerned about is how charge 4 is moving. So my direction on charge 4, because of charge 5, is to the right. Now we have to find the force on charge 4 because of charge 9. So I'll label that as F49. the force on charge 4 because of charge 9. So we have Coulomb's law, KQ4, Q9, divided by my distance squared. So my notation allows me to just put in 4 times 10 to the negative 6. Again, micro is negative 6. And we're going to leave out the negatives. The negatives seem to just cause problems. They don't help us with direction at all. So I know it's a negative 9 microcoulomb, but we just put in all positive numbers into our formula. So divide this by my distance, and so my distance between them from 5 to 8 is 3 centimeters. But we need to change that to meters. So this will become 0.03 meters, and don't forget to square that. So the force on charge 4 because of charge 9 is 359.6 newtons, but we need a direction. So I go back here, and they're the same, or I'm sorry, they're opposite charges. And so they're going to attract each other. So if they attract each other, charge 4 would move towards charge 9, and charge 9 would move towards charge 4. But all I'm concerned about is charge 4. So I see my direction on charge 4 is to the right. I don't care what charge 9 is doing. All I care about is that charge 4 is moving to the right because of that interaction. Now I need to find the total force. So the total force on charge 4, so sigma is again total force on charge 4. We have 2 forces both to the right. Now I'll put in my positive or negative for my directions. So to the right is positive 71.9 plus, and again this is to the right, so it's a positive 359.6. This gives me a total force on charge 4 of 431.5. Units would be newtons. Now my overall total is positive, which means that it's to the right. So again, leave out the positives and negatives. Watch out that you're in the correct units, regular coulombs and meters, not micro or nano or centi or anything like that. And for direction, I put a box around which one I'm looking for, and I only focus on that for my direction.